the disappointing truth about 3I Atlas. 4 months, this interstellar object fueled enormous expectations, ambitious theories, and an almost viral enthusiasm among astronomers and enthusiasts alike. Its greenish coloration, its apparently elongated shape, and the first spectral data led many to believe that we were facing a visitor as enigmatic or as active as Borisov. However, as observatories began to send more precise measurements, the narrative changed abruptly. What many had imagined as an extraordinary body, full of anomalies and unusual behaviors, started to reveal signs that were far from exceptional. That transition from initial wonder to a colder reality generated a collective feeling of disappointment that few were prepared to face. The first processed images showed bright cracks, irregular structures, and contrasts that seemed to suggest unique phenomena. Yet, when the photometric data were evaluated with more sensitive instruments, it became clear that much of those details did not correspond to real physical features, but rather to artifacts generated by saturation, filters, and digital enhancement techniques. What many thought were internal ruptures or active fragmentation turned out to be an exaggerated interpretation of incomplete information. Even so, the greatest impact did not come from the visual errors, but from the direct comparison between what had been imagined and what science ultimately confirmed. 3I Atlas showed no extraordinary signs of composition, displayed no unusual activity, revealed no impossible shapes, and exhibited no behaviors that contradicted existing models. What emerged from the analyses was something much simpler, something that shattered global expectations, an interstellar object that, despite its rarity, did not challenge any scientific framework. And that is precisely where the truth many considered disappointing begins. From the moment 3I Atlas was announced, thousands of people expected this object to redefine what we know about interstellar visitors. Its origin outside the solar system automatically placed it on a pedestal of scientific curiosity, and every update generated a new cycle of speculations, theories, and comparisons with previous discoveries. However, science moves at a different pace from popular enthusiasm, and little by little details emerged that did not always match the initial excitement. Instead of becoming an indecipherable mystery, 3I Atlas ended up revealing characteristics that fitted known patterns, which greatly reduced the drama that had been built around it. It is important to understand that an interstellar object does not need to be extraordinary to be valuable to science. Every visitor provides us with information about remote regions of the galaxy, about processes that occur far from the Sun, and about materials we cannot normally study directly. But when public expectation points toward the spectacular, reality can seem simpler than many would like. The disappointment does not arise from a lack of science, but from the contrast between imagination and actual data. Before delving deeper into the disappointing truth about 3I Atlas, there are 3 things you need to do right now to support honest and rigorous scientific discussion. First, please like this video because that helps bring calm, evidence-based analysis to more people who are tired of sensationalism. Second, subscribe and turn on notifications so you never miss the latest updates on interstellar objects and the real lessons they teach us. And third, head to the comment section right now and simply write the 3I Atlas to join the registry of those who value scientific sobriety over hype and are ready to face the universe exactly as it is. Please do these 3 things immediately. It only takes a few seconds and makes a real difference. The excitement surrounding 3I Atlas did not arise out of nowhere. It was built from a combination of preliminary observations, comparisons with previous interstellar objects, and a global environment eager to find something that challenged existing models. From the beginning, many researchers hoped this visitor would reveal unprecedented clues about distant regions of the galaxy, especially because interstellar objects are not common, and each one carries a physical and chemical signature that can differ greatly from what we are used to seeing in bodies bound to the Sun. When the first instruments detected its brightness and trajectory, an avalanche of interpretations emerged that depended more on enthusiasm than on consolidated data. The possibility that 3I Atlas might display unusual activity, complex internal structures, or even a highly elongated shape began to spread virally, creating an atmosphere of almost global anticipation. The comparison with Oumuamua arose immediately. That object had challenged models with its non-gravitational acceleration, its atypical reflectance, and its apparently extreme geometry. Therefore, any hint of unconventional behavior in 3I Atlas was enough to spark expectation. What many did not consider at the time was that accurately assessing an interstellar object requires repeated observations, stable photometric measurements, and spectral analysis capable of separating the effects of digital processing from authentic physical features. During the first days of observation, images with low detail were obtained, exposed to noise, saturation, and interpolation effects that could lead to mistaken conclusions. Nevertheless, the global community, especially on social networks, began interpreting those low-resolution images as evidence of extraordinary characteristics. One of the most frequently mentioned elements in the initial stage was the supposed intense green color that many claimed to see in the images. Although certain compounds such as diatomic carbon can produce greenish emissions under specific conditions, most representations exaggerated this effect due to visual processing. Professional observatories constantly clarify that the colors shown in public images are usually combinations of filters, calibrations, or multilevel compositions, not faithful captures of the original spectrum. Even so, the widespread perception was that 3I Atlas displayed an anomalous green glow, making it seem exotic and potentially unique among the interstellar visitors detected so far. Another point that heightened the excitement was the impression that it possessed an extremely elongated shape, something that inevitably evoked Oumuamua. The first light curves showed periodic variations interpreted by some as signs of irregular or significant rotation. But those curves were obtained with limited observation windows, without adequate control over instrumental dispersion, and with error margins too large to support any conclusion. When observatories with greater sensitivity began taking more precise measurements, the amplitude of the light curve decreased notably, indicating that the shape might be less extreme than believed. The enthusiasm also grew due to the possibility that this visitor might exhibit unusual cometary activity. Some of the first images that circulated showed what appeared to be bright cracks or possible emission zones, but subsequent scientific analysis revealed that these supposed patterns were artifacts caused by the combination of saturation, electronic noise, and automatic contrast adjustments. Interstellar objects can show cometary activity if they contain ice that sublimates as they approach the Sun. However, the initial spectral data for 3I Atlas did not confirm significant rates of gas release. The lack of solid evidence indicated that the signals detected in the early images did not correspond to real physical activity, but rather to technical limitations. As the analyses progressed, expectations inevitably began to confront reality. The object, though intriguing due to its interstellar nature, showed no signs of challenging established models. The idea that it might be a fractured, unstable body in the process of disintegration began to lose strength when observatories with better instruments detected a more consistent brightness curve and a structure without notable anomalies. The collective disappointment did not occur due to a lack of science, but because of the contrast between what many expected and what the data actually showed. The scientific community, accustomed to working with margins of uncertainty and following strict protocols, understood from the start that the first observations were not sufficient to support extraordinary claims. However, for those seeking a new cosmic mystery, the reality proved less exciting than imagined. 3I Atlas, despite its importance as a messenger from distant regions of space, showed no signs of behaving like an exceptionally rare object. Rather, it aligned with chemical and photometric characteristics compatible with similar bodies observed within the solar system. Its brightness, when analyzed correctly, revealed patterns consistent with relatively common materials in comets and asteroids. Its dynamic behavior exhibited no unexpected alterations or non-gravitational accelerations. The expectation of an unpredictable and extraordinary body quickly faded as data accumulated and scientific understanding strengthened. This process of transition from collective illusion to clarity based on measurements forms the heart of the initial perception of 3I Atlas. The disappointing truth does not lie in a lack of scientific value, but in the fact that its behavior fits within parameters we already know, without offering features that break models or challenge theories. And it is precisely this understanding that opens the way to analyzing in detail what was discovered later and why so many people felt their expectations were not met. As instruments with higher resolution began studying 3I Atlas, it became clear that much of what was seen in the early days had been a combination of technical limitations and public expectations. The scientific community needed more precise data to evaluate the real behavior of this object, and that could only be achieved through repeated observations under different lighting conditions, distances, and atmospheric stability at ground-based telescopes. The first spectral analyses arriving from professional observatories revealed a more sober truth. The photometric signals that many had interpreted as exotic features were, in reality, consistent with particles common in icy and rocky bodies. There were no indications of extremely rare compounds or unknown physical processes, which began to deflate the sensationalist narratives that had emerged before the data were complete. One of the most important steps in understanding the nature of 3I Atlas was to review its spectrum precisely, identifying the wavelengths that dominated its emission. Observatories recorded patterns compatible with compounds present in standard comets: diatomic carbon, cyanogen, and simple organic molecules. These signals were not extraordinary and matched what would be expected from a body that had traveled through interstellar space for millions of years. Although certain elements could explain the apparent greenish tone observed in popular images, professional analysis indicated that this coloration was much less intense in reality and had often been exaggerated by automatic enhancement algorithms used to improve contrast in low-exposure photographs. This type of visual processing, while useful, can generate incorrect interpretations. When presented to the public without technical explanation, it leads to misunderstanding. The strict evaluation of the light curve of 3I Atlas also played a crucial role. Light curves are fundamental tools for studying the rotation and approximate shape of a celestial body. When periodic variations in brightness are detected, it is usually interpreted as evidence that the object has irregularities or a non-spherical geometry. However, to reach solid conclusions, multiple measurements taken from different orbital angles are necessary. In the case of 3I Atlas, the first recorded curves had considerable scatter, creating the illusion of extreme variation. When more sensitive telescopes were able to observe it over longer intervals with better atmospheric corrections, the amplitude of these variations decreased significantly. This indicated that the object did not have such an elongated shape or irregular rotation as initially suggested. In other words, the first impression was misleading due to insufficient observations. Something similar happened with the supposed internal structures that appeared in images spread on social media. Many users believed they saw bright fractures, tension lines, or emission zones that seemed to indicate unusual activity. But when scientific analyses processed those same images with calibrated filters, it became evident that those patterns did not correspond to physical features. They were the result of electronic noise, interpolation errors, and effects produced by cameras with low-sensitivity sensors trying to capture an extremely faint object under suboptimal conditions. The public interpreted these artifacts as striking signals, but from a scientific viewpoint, there was no evidence that 3I Atlas was fragmenting, overflowing with activity, or displaying unique structural characteristics. On a dynamic level, another aspect that caused confusion was the object's trajectory. When it was announced that its origin was interstellar, many people assumed its orbit had to be highly atypical. However, the classification of an interstellar body does not depend on a rare orbital shape, but simply on its eccentricity being greater than 1, indicating it is not gravitationally bound to the Sun. In other words, an open trajectory is sufficient to confirm it comes from interstellar space. In the case of 3I Atlas, its orbit was perfectly consistent with what is expected of an object crossing the solar system, with a characteristic velocity influenced by large-scale galactic forces. Its passage did not challenge gravitational models nor show unexplained accelerations, thus ruling out any premature comparison with anomalies like those seen in Oumuamua. Cometary activity measurements also dispelled several initial myths. In the early days, some observers claimed to see signs of active jets or intense sublimation, but this was ruled out when professional instruments analyzed dust dispersion and gas emission. Sublimation was rather light, compatible with moderate temperatures and standard behavior for an interstellar body composed of ice hardened after millions of years without significant solar radiation. This explained why it showed no strong activity that many expected. The volatile material was likely degraded or present in reduced quantities after such a long time exposed to the interstellar medium. The lack of intense activity was not a sign of rarity, but a natural consequence of the physical wear accumulated along its galactic trajectory. Furthermore, the analysis of its total brightness showed that 3I Atlas did not contain extraordinary amounts of dust or fresh ice. This helped debunk the idea that it was a newly formed object or undergoing a destabilization phase. Each more precise measurement reinforced the idea that its characteristics aligned with those observed in ancient icy bodies, hardened and with surfaces processed by cosmic radiation over extended periods. The photometric behavior was stable, without sudden oscillations, without eruptive events, and without signs of massive detachment. The progress of these detailed observations strengthened the general conclusion. What many interpreted as extraordinary signals were, in reality, features completely compatible with common solar system bodies transported into an interstellar context. The disappointment arose because expectations had been inflated by preliminary images and hasty comparisons. Science, in contrast, proceeded cautiously, applying rigorous protocols that gradually cleared away visual illusions and replaced them with solid information. Thus, the stage analyzed in this part reveals an important lesson. A preliminary image should never be taken as definitive proof of an unusual phenomenon. 3I Atlas did not show the extraordinary that many imagined, but rather how consistent an interstellar traveler can be after traveling such an extensive path through an environment as hostile as deep space. And it is in that consistency, not in sensationalism, where its true scientific value lies. When the most complete spectral analyses of 3I Atlas began to arrive, scientific attention focused on understanding its composition as accurately as possible. Interstellar objects are important because they function as physical fragments from remote regions of the galaxy, places we cannot visit or observe in detail. Every molecule, every spectral pattern, and every thermal behavior reveals processes that occurred outside the solar environment. That is why expectations about the composition of 3I Atlas were so high from the beginning. Many imagined that, coming from another star system, its chemical structure might include exotic components, complex organic materials, or even uncommon isotopes. However, as measurements advanced, reality became much more sober. The first low-resolution spectra suggested a possible presence of compounds that some interpreted as unusual, but those initial readings were full of noise and had insufficient resolution to confirm any extraordinary signal. When observatories equipped with high-sensitivity spectrographs obtained clearer data, the spectral peaks showed familiar patterns, bands associated with diatomic carbon, cyanogen, simple hydrogen molecules, and organic fragments found in ancient comets. This did not mean the object was identical to a solar system comet, but its composition was far less exotic than many expected. Detailed analysis of these signals showed that 3I Atlas was composed of materials that had undergone long periods of cosmic irradiation and typical molecular fragmentation processes for a body that traveled for millions of years through the interstellar medium. Galactic radiation alters the surface of objects, degrading volatile compounds and transforming outer layers into a hardened crust rich in dark carbon. These characteristics matched what was observed in the spectrum: clear signs of prolonged chemical erosion, but no traces of complex molecules that might indicate exceptional phenomena. The lack of unusual components puzzled those who expected an interstellar visitor to display chemistry completely different from traditional comets. But from a scientific perspective, this is highly consistent. Theoretical models suggest that many icy bodies outside the solar system form very similarly to ours, following universal processes guided by molecular physics and protoplanetary disk conditions. Although chemistry can vary slightly depending on the parent star and formation environment, the overall structure tends to repeat certain patterns, especially in simple materials such as hydrocarbons, silicates, and ices of water and carbon dioxide. The hope of finding something drastically different was more a public expectation than a well-founded scientific prediction. Another important point of the analysis was the firmness of the surface. Some researchers initially raised the possibility that 3I Atlas had a heterogeneous crust or internal fractures that could lead to irregular emissions or unexpected activity. However, when reflected light dispersion was evaluated, it became clear that the object's reflectance was low and homogeneous, consistent with a surface darkened by long periods of exposure to the interstellar medium. This type of surface tends to absorb more heat but release less reflectance, which would explain why some images showed exaggerated contrasts. The homogeneity in reflectance also indicated that the object did not present major compositional variations across its different areas, contradicting the initial idea that it was formed from exotic materials mixed or irregularly distributed. Even expectations about complex organic compounds faded when the spectra were reviewed with greater precision. Signals compatible with simple organic molecules were detected, but no strong indication of more advanced structures. This was not a disappointment from a scientific viewpoint, because complex molecules rarely survive intact after millions of years of cosmic radiation. However, for the public that expected an interstellar visitor with extraordinary characteristics, this news reinforced the idea that 3I Atlas was less impressive than anticipated. The object's thermal analysis also supported the conclusion that its composition was not extraordinary. As 3I Atlas approached the Sun, instruments measured the heating rate and thermal response of its surface. A body with rare compounds might show unusual thermal behavior, but 3I Atlas displayed a pattern completely consistent with common materials. The sublimation rate was low, suggesting that the content of volatile ices was reduced or had completely degraded during its interstellar journey. This matched the idea that the object had lost much of its most sensitive material before entering the solar system. Its thermal activity aligned with observations made on ancient comets that have repeatedly passed near the Sun, even though in this case it was a body that had never been in this environment. At a structural level, the spectral signals showed no indications of unusual minerals or metallic compounds in notable quantities. The absence of characteristic peaks for rare materials reinforced the conclusion that 3I Atlas was a body composed mainly of common compounds, hardened by the passage of time. Even the apparent density, estimated from how it reflected light and its dynamic behavior, suggested a relatively solid internal structure, without extensive cavities or extreme weakness zones. This debunked the idea that it could easily fragment or show erratic behaviors. Thus, the chemical and structural analysis of 3I Atlas made clear that the object, although originating from an unknown region of the galaxy, did not present characteristics that challenged existing models. Its composition was consistent. Its surface was predictably processed by deep space, and its thermal behavior followed standard patterns. The real disappointment arose because many expected to find a visitor full of rarities, an object capable of revolutionizing science. But what science found was an interstellar body that fits perfectly within current understanding, a silent and resilient messenger shaped by millions of years of travel. The value of 3I Atlas does not lie in the extraordinary, but in what it confirms. The physical and chemical processes that govern the formation of icy bodies appear to be universal. This understanding is actually one of the most important results an interstellar object can offer, even if for some it is disappointing that it does not break models. Its existence strengthens the idea that the fundamental principles of astronomy apply far beyond the solar system. The idea that 3I Atlas possessed an extraordinarily elongated shape became firmly established in public conversation very early on, long before robust data existed that could either support or rule out such a possibility. The first light curves taken with telescopes operating under unfavorable lighting conditions and with observation windows that were far too short showed brightness variations that many interpreted as unequivocal signs of extreme elongation. However, light curves are extremely sensitive to instrumental interference, atmospheric variations, and exposure limitations. Those initial fluctuations were not sufficient to calculate the true geometry of the object, although they were enough to fuel hasty comparisons with the unusual shape associated with Oumuamua. When higher quality data began to accumulate, the story changed completely. A truly elongated object displays very marked and repetitive brightness variations, with predictable amplitudes that reflect its rotation and the amount of light it reflects as it exposes different surfaces to the observer. In the case of 3I Atlas, the detected variations decreased significantly when observations were standardized with longer exposure times, more sensitive sensors, and proper atmospheric corrections. The amplitude, which initially seemed large, dropped to values compatible with objects that have mild irregularities or rough surfaces, but not with extremely elongated structures. This reduction in amplitude not only contradicted the idea of an extreme shape, but also showed that the first interpretations were distorted by noise and photometric scatter. The low-resolution images that circulated on social networks also contributed to the mistaken narrative. Most of these images were obtained in low-light conditions, forcing instruments to perform pixel interpolation to generate a visual representation. This process can create the illusion of elongation, especially when a point-like object is stretched by imprecise tracking movements or when automatic sharpness enhancements are applied. Many believed they saw an elongated body because the edges extended due to telescope movement, vibrations, or imperfect alignment techniques. When professional observatories reviewed those images and applied proper calibrations, the supposed elongations disappeared, revealing a more compact structure consistent with medium-sized icy objects. The detailed analysis of light scattering also helped clarify the true nature of the shape of 3I Atlas. If an object is highly irregular, especially if elongated, the reflected light changes abruptly as it rotates. One would expect to see sudden jumps in the light curve reflecting contrasts between wider and narrower areas, but instruments that captured complete rotation series found that the scatter was smoother than expected for an extreme shape. This indicated that the body could be moderately irregular, as most comets and asteroids are, but did not display the variation patterns characteristic of a bifid or extremely elongated object. Another element that confused public perception were images showing a supposed elongated tail or extended filaments. Many interpreted these structures as part of the physical body, when in reality they were dust and gas emissions or even star trails appearing in photographs with long exposure times. When an object is very faint, background stars can leave trails when registered with tracking movements, generating linear shapes that seem connected to the object but have no physical relation to it. Additionally, some images presented halos produced by internal scattering in optical instruments, something that can alter the appearance of the object's edge without representing its true shape. Shape precision is also obtained through indirect estimates such as the study of angular momentum. If 3I Atlas had truly been very elongated, its rotation would have produced detectable oscillations or vibrations. Objects with extreme geometries tend to show complex periodic changes in their light, resulting from peculiarly distributed angular momenta. However, the collected data showed a stable rotation pattern, without signs of strong vibrations or irregularities that would contradict a relatively compact body. This reinforced the idea that the shape was not extraordinary or indicative of unusual phenomena. Even the object's orientation contributed to the initial confusions. In the early days, the relative geometry between the Sun, Earth, and 3I Atlas caused some reflections from its coma, though weak, to align with the terrestrial viewing angle, producing a slight apparent elongation. This type of angular effect is common in small dark objects that lack sufficient brightness to generate defined images. As days passed and the viewing angle improved, those elongations disappeared. This is further evidence that what was initially observed did not correspond to the real shape, but to temporary geometric effects. The lack of extreme elongation also does not contradict its interstellar origin. Although Oumuamua showed uncommon characteristics, there is no rule stating that all interstellar objects must possess exotic geometries. In fact, current models suggest that interstellar objects can have shapes similar to those of solar system bodies, because they form under comparable physical processes. Collision forces, fragmentation, and compaction act universally in protoplanetary disks and produce bodies with moderate irregularities, not necessarily extreme structures. That is why the popular expectation that 3I Atlas had to have a spectacular silhouette was a reflection of the media influence of previous discoveries, not a scientifically grounded assumption. Over time, the image of 3I Atlas as an exotic object faded and gave way to a more sober and realistic portrait. A medium-sized interstellar body with eroded surfaces, without extreme elongations and with stable rotation. This does not diminish its scientific importance. On the contrary, it provides a valuable comparison point for understanding the diversity of objects that can cross the solar system. The existence of an interstellar visitor that does not challenge models but fits within them demonstrates that the formation of icy bodies follows universal principles that repeat beyond our planetary borders. The expectation of finding impossible shapes or striking geometries reflected more a collective desire than a scientific prediction. Science, with its careful measurements and methodological rigor, showed that reality is different. The shape of 3I Atlas is consistent, stable, and compatible with millions of years of interstellar erosion. That consistency may be disappointing for some. However, for those studying the physics of small objects, it represents an extraordinary opportunity to confirm models and discard hypotheses based on premature visual interpretations. One of the elements that most fascinated and confused the public regarding 3I Atlas were the supposed jets, green filaments, and long structures that seemed to emerge from the main body in different directions. Many interpreted these features as signs of extraordinary activity, as if the object were violently releasing materials or exhibiting behaviors typical of an extremely active comet. However, as professional observatories analyzed these traits with greater precision, it became clear that what appeared so surprising in popular images had much more sober and scientific explanations. The key was to differentiate between a real physical phenomenon and visual effects generated by instrumental conditions, extreme processing, or even mistaken interpretations. To understand this point, it is essential to remember how comets and icy bodies behave when approaching the Sun. Ice sublimation produces gas emissions that drag dust particles, creating tails visible from great distances. These tails can take different shapes depending on the object's rotation speed, the size of expelled particles, and interaction with the solar wind. Nevertheless, in the case of 3I Atlas, spectral measurements indicated that sublimation was extremely low, making it unlikely that it was generating powerful jets or very defined filaments. In fact, later analyses showed that many of the patterns seen in early images were processing artifacts or saturation effects rather than real physical structures. One of the most common phenomena that generate visual confusion in astronomical records is the presence of halos and overexposure around very faint objects. When an interstellar body is captured in low light conditions, telescope sensors can amplify the signal to try to obtain a clearer image. This process, while useful for detecting weak objects, can also exaggerate details or create luminous patterns that resemble filaments or active tails. In the case of 3I Atlas, professional observatories verified that the supposed green filaments were not physical structures expelled from the nucleus, but amplified regions where the diatomic carbon signal was overexposed, generating a deceptive visual effect. Moreover, many of the records shared on social networks came from small telescopes, digital single-lens reflex cameras, or instruments not professionally calibrated. These tools, though valuable for amateur astronomy, lack the resolution or photometric control to distinguish between a real jet and electronic noise. When an image is taken with prolonged exposure times, any movement or atmospheric variation can produce trails that simulate long, thin structures. This explains why some observers claim to see jets pointing in inconsistent directions or extending more than would be physically possible for such a faint object with limited activity. Another key factor in the mistaken interpretation of filaments was the interaction of the solar wind with small amounts of gas present around the object. Even when sublimation is weak, ionized gas particles can be pushed by the solar wind, forming ion tails that sometimes appear as straight lines or narrow filaments. However, these tails are usually extremely faint and require specialized instruments to be properly recorded. In the case of 3I Atlas, professional observations confirmed that any emission of this type was too weak to create structures visible in popular images. In other words, what the public believed they saw did not match what scientific instruments detected. The geometry of the object, combined with its orientation relative to the Sun and Earth, also played an important role in the initial confusion. In certain configurations, lighting can generate shadows, gradients, or reflections that simulate structures extending from the nucleus. This occurs especially when the object's surface is rough or has irregular textures. However, light scattering analyses of 3I Atlas showed no variations indicating the presence of protruding structures or protuberances that could generate defined shadows. This reinforced the idea that the observed filaments had no real physical basis. Another important aspect was the public's tendency to interpret processed images as if they were faithful representations of the object. Astronomical images are almost never presented exactly as they come from the telescope. In most cases, they undergo contrast adjustment, noise reduction, color calibration, and composition of multiple exposures. These techniques are essential to reveal details that would otherwise be invisible, but they can also produce visual effects that the human eye interprets incorrectly. In the early days of 3I Atlas, many intensely processed images were shared without context, leading to exaggerated interpretations of its activity. Specialists who reviewed those records confirmed that the supposed giant jets did not hold up when the object was analyzed with standard calibrated filters. Even some popular videos showing the object in motion had digital compression issues. Compression can generate linear artifacts that appear to move with the object, giving the illusion of dynamic filaments or pulsating tails that are actually file defects. When astronomers compared these videos with professional raw records, the moving filaments disappeared completely. The true nature of the jets and tails of 3I Atlas turned out to be consistent with that of a worn interstellar body, with little activity and limited volatile materials. The small amount of detected sublimation was enough to explain weak and diffuse emissions, but not complex or prominent structures. In fact, that low activity was one of the factors that led scientists to conclude that the object had lost much of its most sensitive compounds during its long interstellar journey, an interpretation that aligns with physical models of erosion in deep space. The disappointing truth about the filaments and jets of 3I Atlas does not lie in the object lacking interest, but in the fact that many popular representations were not faithful to physical reality. Science showed that what was attributed to extraordinary phenomena was, for the most part, the product of visual effects, mistaken perceptions, or excessive processing. What really existed around the object was a weak emission perfectly consistent with an ancient icy body that retained little activity. This finding redefined public understanding and eliminated the mystery many believed they had discovered. Ultimately, the detailed study of the jets and filaments helped strengthen the scientific understanding of the object, even though it reduced the initial drama. Astronomy, by applying its rigorous methodology, revealed that the activity of 3I Atlas was modest, consistent, and predictable. And although this disappointed those seeking a cosmic spectacle, it also confirmed something fundamental. Even interstellar visitors obey universal principles of physics and chemistry, strengthening the theoretical foundation for studying similar future objects. One of the aspects that most surprised scientists, though in a way completely opposite to what the general public expected, was the low activity of 3I Atlas. While many imagined that an interstellar object approaching the Sun for the first time would release large amounts of gas and dust due to sudden heating, measurements showed extremely moderate behavior. This contrasted radically with the initial expectations disseminated on networks and non-specialized media, where it was claimed that 3I Atlas might experience energetic eruptions, intense jets, or an abrupt increase in brightness. None of that happened. On the contrary, the object showed signs of being a deeply worn body, with a significantly reduced reserve of volatiles and a stability that surprised those expecting a cometary spectacle. To understand this apparent lack of activity, it is necessary to analyze the probable origin and history of an interstellar object. Unlike solar system comets that preserve some of their internal ices thanks to measured thermal cycles, interstellar bodies spend millions of years exposed to the galactic medium, background radiation, and particle impacts that degrade their most sensitive compounds. This means that when they finally enter a star system, they have usually lost much of their volatile material. 3I Atlas, according to spectral measurements, had little quantity of compounds that could easily sublimate. This explains why it showed no significant jets or sudden brightness increases, even when reaching higher temperatures near the Sun. Thermal records also demonstrated that the object reacted slowly to the increase in solar radiation. Objects with abundant ice respond quickly, generating visible halos and detectable emissions from moderate distances. In contrast, 3I Atlas showed a smooth thermal curve, without sudden sublimation peaks. This is characteristic of hardened surfaces coated with dark carbonaceous materials that act as insulators and reduce the outward flow of gases. Such a surface not only decreases activity but also stabilizes overall behavior, something observed in its brightness curves and the absence of fragmentation or massive detachments. The low activity was also reflected in the lack of a prominent coma. Under normal conditions, a young comet or one rich in volatiles generates a diffuse atmosphere around the nucleus, visible even in medium telescopes. In the case of 3I Atlas, the coma remained extremely faint, making observation with small instruments difficult and increasing the tendency for its image to be misinterpreted. Many believed they saw fragments, jets, or irregular emissions, but those interpretations arose from noise and exaggerated processing, not real activity. The object was actually releasing minimal amounts of gas insufficient to generate large or distinguishable structures. Another key indicator of low activity was the stability of its nucleus. Highly active objects usually experience sudden changes in luminous intensity due to rupture events or gas releases from internal regions. However, 3I Atlas showed extremely stable behavior with variations remaining within expected parameters for a solid and aged body. This contradicted initial theories suggesting it might disintegrate as it approached the Sun, as occurred with other comets in extreme orbits. Instead, it remained compact without signs of significant internal stress. The low activity also surprised because the object was approaching the Sun for the first time. In theoretical models, a fresh interstellar visitor should react intensely to thermal change. However, recent studies indicate that many interstellar objects do not retain enough volatile material to behave like traditional comets. Cosmic radiation degradation and constant particle impact tend to reduce porosity and increase surface density. This causes any remaining internal volatiles to be released slowly through microfractures, without generating visible explosions or intense tails. The interaction of 3I Atlas with the solar wind was also weaker than expected. Charged particles flowing from the Sun usually drag ionized gases and form ion tails. But for these tails to be visible, a minimum amount of emission is needed, which the object simply was not producing. Spectral records showed light emissions compatible with ionized particles, but at intensities so low they could barely be distinguished from the background. This reinforced the idea that the object had weak activity and that any visual structure attributed to prominent jets was a misinterpretation. Even the total brightness of the object reflected its lack of activity. Comets that activate strongly show a rapid magnitude increase as they approach the Sun. 3I Atlas, in contrast, maintained a moderate brightness curve without abrupt increments, consistent with ancient icy bodies that have already lost nearly all their sublimable materials. This stability challenged popular expectations but fitted perfectly with modern scientific understanding of interstellar erosion. The disappointing truth about its activity does not lie in a lack of interest, but in the contrast between expectation and reality. Many expected a spectacular visitor full of energy and visible phenomena, but 3I Atlas showed silent, stable, and scientifically consistent behavior. Its low activity is not a flaw but a testament to its longevity. What the public interpreted as a lack of excitement, scientists interpreted as crucial confirmation. Extreme where processes in deep space shape interstellar objects until they become resistant, dim, and predictable. In essence, the activity of 3I Atlas was much lower than anticipated because its history was far longer than imagined. The object did not arrive in the solar system as a youthful body loaded with energy, but as an ancient fragment polished by millions of years of travel. That is the reason behind its calm behavior, its weak tail, and its lack of impressive jets. Instead of being a spectacle, it was a reminder of the harshness of the interstellar medium and how physics always prevails over human expectations. When 3I Atlas was first detected, a series of forecasts based on preliminary data were published. These forecasts spread rapidly and were often interpreted as almost guaranteed projections, even when scientists warned it was too early for definitive conclusions. Among the expectations set in that initial phase were the possibility of a sudden brightness increase, the appearance of intense cometary activity, the formation of a pronounced tail, drastic changes in rotation, and even eventual fragmentation near perihelion. However, as the scientific community obtained more complete and precise measurements, most of these predictions did not come true. This led to a gap between what was expected of the object and what actually happened. One of the most circulated forecasts was that 3I Atlas would experience a pronounced brightness increase as it approached the Sun. This behavior is typical in comets with abundant volatiles that react quickly to increased solar radiation. When it was announced that the object was interstellar, many automatically assumed it would have fresh material never previously heated, implying it should activate even more intensely than a typical solar system comet. However, this expectation ignored a crucial point. Interstellar objects are not necessarily fresh. In fact, they are usually more degraded than comets that periodically orbit the Sun. Later spectra confirmed that the object's volatiles were scarce, explaining its moderate and stable brightness. There was no dramatic increase, no explosions of activity, only a gradual variation compatible with slight surface heating. Another widely disseminated forecast suggested the object might fragment as it approached perihelion due to extreme thermal stresses. This behavior has been observed in weakened comets whose nuclei broke into multiple pieces before reaching perihelion. Many extrapolated this pattern to 3I Atlas without considering that interstellar medium erosion mechanisms do not necessarily leave fragile structures. In some cases they generate hardened surfaces and extremely compact nuclei. As observatories followed its trajectory, the object was observed to maintain surprising integrity. There were no visible ruptures, no detected detachments, and spectral signatures remained stable. The fragmentation forecast turned out to be unfounded, based more on hasty comparisons than solid evidence. It was also expected that 3I Atlas would develop a long and visible tail comparable to highly active comets. Initial images taken with non-professional equipment and intense processing seemed to show filaments that many interpreted as an emerging tail. However, when professional measurements accumulated, it became clear that the object's real tail was extremely faint. The level of released dust particles was minimal, insufficient to form a prominent structure. The solar wind, interacting with small amounts of ionized gas, may have generated an almost imperceptible ion tail, but it was never intense enough to match popular expectations. Another forecast that did not materialize was related to its rotation. In the early days, some poorly interpreted light curves suggested the object might be rotating chaotically with possible vibrations or irregularities indicating extreme geometry or internal stresses. When higher quality photometric series were obtained, it was verified that rotation was stable and brightness variations remained within moderate parameters. This refuted expectations that the object might exhibit sudden behavioral changes or dynamic instabilities. Its calm rotation aligned much more with a massive and solid body than with a highly irregular or fractured one. There were even predictions regarding possible unexpected chemical signatures. Some expected 3I Atlas might contain exotic compounds not commonly found in the solar system, generating speculation about complex molecules or advanced organic structures. But when high-resolution spectra were analyzed, detected compounds were consistent with simple hydrocarbons and common carbon fragments. There were no signs of extremely unusual chemistry. This contradicted the expectation that an interstellar object must necessarily bring totally different materials from those known. An additional forecast anticipated that interaction with the solar wind would be more intense. Some believed it might exhibit distorted tails, rapid ionization variations, or even stronger interactions with the solar magnetic field. But data showed the object released minimal gas, significantly limiting any such interaction. Weak ionization indications were detected, but not at the magnitude many expected. The interaction was so slight that in many cases it was difficult to separate the object's signal from the background. Perhaps the most notable discrepancy between forecasts and reality was the general expectation that 3I Atlas would be an object revealing anomalies, as occurred with Oumuamua. But that expectation was built more by media narrative than scientific projections. The simple fact that it was an interstellar visitor was enough for many to assume it had to challenge models or generate deep debates. However, when examined with rigorous tools, the object fitted perfectly within known parameters. There were no unusual non-gravitational accelerations, no inexplicable trajectory changes, no signals indicating extraordinary behavior. Its passage through the solar system was scientifically valuable but not extraordinary. This disconnection between popular forecasts and scientific measurements led to a general feeling of disappointment. However, from a scientific perspective, 3I Atlas fulfilled something important. It showed that interstellar objects can be normal. This is crucial because it confirms that formation processes in other regions of the galaxy follow universal principles. Science is enriched not only by the extraordinary but also by the consistent. Objects like 3I Atlas allow model comparison and theory refinement without needing extreme phenomena. Ultimately, the unfulfilled forecasts demonstrate how expectations can distort the perception of a discovery. What was expected of 3I Atlas did not match what it really was, generating a narrative of disappointment. But the true importance of the object does not depend on fulfilling dramatic expectations, but on strengthening scientific understanding of interstellar travelers and how time and radiation shape solid bodies in deep space. The final understanding of 3I Atlas did not come from a single discovery, but from the consistent accumulation of data from observatories in different countries, instruments with varying sensitivities, and carefully compared spectral analyses. When all that information was reviewed together, it became clear that the so-called disappointing truth about the object did not arise from scientific error, but from the contrast between what the public expected and what science actually found. 3I Atlas showed no extraordinary phenomena, did not break models, offered no unexpected signals, and presented no characteristics challenging current understanding of interstellar travelers. What emerged from the investigation was a sober and consistent portrait of a body that had spent millions of years traveling through deep space. Worn, silent, and stable? The chemical part of this truth was one of the most conclusive. Spectra obtained from different observatories showed very clear patterns. Emissions associated with diatomic carbon, cyanogen, simple organic fragments, and carbonaceous particles darkened by radiation. These components are extremely common in old comets within the solar system, contradicting the initial narrative claiming the object might contain exotic molecules or unknown materials. The absence of extraordinary chemical signals was not a scientific failure. It was confirmation that erosion and photodissociation processes in the interstellar medium act uniformly, degrading complex compounds and leaving hardened, chemically simple surfaces. This type of result is valuable because it demonstrates that current models of deep space chemistry remain accurate. Another aspect contributing to this sober truth was the evident lack of significant activity. At first, many believed an interstellar object approaching the Sun for the first time should react dramatically, releasing large amounts of gas like a newly activated comet. But data showed the opposite. Activity was extremely weak. 3I Atlas barely sublimated a minimal amount of volatiles, perfectly matching a body that had spent millions of years exposed to galactic wind, energetic particles, and cosmic radiation. This long-term degradation drastically reduces an object's capacity to produce visible jets or halos. Science already expected this as a possibility. What failed were popular expectations imagining a highly dynamic and spectacular interstellar visitor. The object's shape also contributed to this perception. Early low-resolution images gave the impression of an elongated and complex structure, but as more precise photometric measurements accumulated, it was verified that 3I Atlas had smooth brightness variations compatible with moderately irregular geometry, not an extreme shape. Highly elongated objects display abrupt and repetitive light changes. But that was not the case. This reinforced the idea that initial images were affected by noise, saturation, or interpolation and did not represent the real structure. What seemed extraordinary was simply a visual illusion created by technological limits. Forecasts about possible dynamic anomalies also collapsed as studies advanced. Some expected non-gravitational accelerations similar to those observed in Oumuamua. But 3I Atlas showed no significant trajectory deviation. Its hyperbolic orbit was totally consistent with an interstellar visitor without additional interaction. Gravitational forces acted predictably without surprises. The same occurred with rotation patterns. There were no signs of chaotic vibrations or instabilities. Rotation was stable, typical of a massive object with resistant internal structure. Even solar wind effects ended up being lesser than some anticipated. Objects with high activity present clearly visible ion tails, but 3I Atlas emissions were so weak they could barely be separated from the space background. This reinforced the idea that processed images showing supposed giant filaments did not reflect the object's physical reality, but visual artifacts caused by enhancement techniques or low-sensitivity sensors. As these scientific conclusions became public, the collective feeling arose that 3I Atlas was disappointing. But that frustration did not come from the data, but from exaggerated expectations built around it. An object was expected that would break rules, offer mystery, bring something never seen. Reality was very different. 3I Atlas confirmed existing models instead of challenging them. It showed that interstellar objects can be quiet, dim, and eroded, without needing extraordinary behaviors to be valuable. From a scientific viewpoint, the real value of 3I Atlas lies in that consistency. Its composition confirms that basic chemical processes forming icy bodies repeat in different star systems. Its low activity confirms that interstellar wear profoundly transforms objects traveling for millions of years. Its moderate shape confirms that extreme geometry is not a universal characteristic among interstellar visitors, and its stable trajectory confirms that gravitational dynamics also impose themselves predictably in these cases. Science does not consider this disappointing. On the contrary, it considers it fundamental. Every interstellar object that behaves consistently with models strengthens understanding of universal physics, showing that solid matter forming around other stars follows rules similar to those in our own solar system. 3I Atlas did not revolutionize theories, but reaffirmed key principles, and that is equally important. Public perception, however, was driven by the expectation of seeing something spectacular. A mystery, an enigma, an anomaly was desired. And since the object offered none of that, the narrative was built that it had failed. But science does not seek spectacle, it seeks truth. And the truth of 3I Atlas was clear. An ancient, silent, worn interstellar body completely within known physical parameters. That is precisely the essence of its disappointing truth. It was not what many wanted it to be, but exactly what physics said it should be. One of the questions that arose most among the public as images of 3I Atlas circulated on the internet was simple yet insistent. If the object was not so extraordinary, why did it look so strange in so many photos? Why did it show irregular shapes, elongated filaments, intense green areas, strange halos, or apparent luminous breaks? The scientific answer to this doubt is not only important for understanding the case of 3I Atlas, but also for comprehending how astronomical images really work and why many times what is seen does not faithfully represent the physical structure of the observed object. The first reason 3I Atlas appeared so strange in photographs has to do with the extreme weakness of its real brightness. The object was faint from the beginning, even before approaching close enough to the sun to become more perceptible. When such a dark and distant object is captured by a digital sensor, the telescope needs prolonged exposure times to accumulate sufficient light. However, long exposures also increase electronic noise, background trails, and distortion introduced by telescope movement. All these factors create patterns that the human eye can interpret as real structures, even though they are not. Moreover, many of the records that went viral on social networks did not come from professional telescopes, but from amateur observers with limited equipment or adapted digital single-lens reflex cameras. These devices, though valuable for amateur astronomy, lack the calibration level that professional instruments use to correct optical defects, internal scattering, or saturated pixels. When such an image is digitally processed to make the object more visible, sharpness, contrast, or noise removal algorithms can produce artifacts that resemble jets, cracks, filaments, or elongations. In the case of 3I Atlas, many of the supposed anomalous features arose precisely from these aggressive processings. Another fundamental factor is the use of color filters. Most astronomical images do not represent colors as the human eye would see them. They are compositions made from specific filters, for example, filters for diatomic carbon, cyanogen, or ionized oxygen emissions that are later combined artificially. When 3I Atlas was photographed using filters sensitive to carbonaceous molecules, regions with even a minimal amount of emission became saturated and acquired exaggerated green tones. This made it seem that the object had an intense and uniform coloration, when in reality that appearance was a product of how sensors respond to certain wavelengths. The object's orientation relative to the Sun and Earth also contributed to creating visual illusions. At certain moments, the exact lighting angle generated gradients that gave the impression of shadows or protruding structures. But light scattering analyses showed that these shadows did not correspond to physical relief, but to areas where light was distributed unevenly due to minor surface irregularities or simply variations in instrument calibration. Another element that greatly contributed to the visual mystery was the phenomenon known as illusory coma. When an object releases very small amounts of gas, light reflected by those particles can create a kind of weak halo. If that emission is too faint to be clearly distinguished, the halo mixes with the background and produces irregular textures that resemble fractures or filaments. Many observed these textures in images of 3I Atlas and concluded they were active jets. However, when analyzing the original images with appropriate filters, astronomers confirmed that those textures were solely amplified noise, even in professional images. 3I Atlas could appear strange due to an optical effect known as internal telescope scattering. This phenomenon occurs when part of the light entering the optical system reflects inside the instrument itself. In bright objects this is insignificant, but in extremely faint objects like 3I Atlas, any internal reflection can create halos or trails that give the impression of non-existent structures. Such trails were repeatedly mistaken for an active tail or extended filaments. Another common problem was digital compression, especially in videos spread on the internet. Video formats reduce the amount of information in each frame to make the file lighter. This process eliminates detail and replaces real information with blocks or lines. In videos of 3I Atlas, these compression artifacts generated linear patterns that seemed to move with the object, giving the impression that it had dynamic filaments or pulsating tails. When astronomers compared those videos with uncompressed raw data, the moving filaments disappeared completely. To all this is added an inevitable psychological factor: the human tendency to seek meaningful patterns even where none exist. When an image shows spots, lines, irregular shadows, or ambiguous textures, the brain tries to interpret them as familiar shapes. This can make observers see jets where there is only noise or elongations where there are merely diffuse edges. In the case of 3I Atlas, this tendency combined with inflated expectations generated mistaken interpretations that spread before scientific data could correct them. Finally, it is important to note that even professional telescopes can produce misleading images if atmospheric conditions are not ideal. The passage of warm and cold air currents in front of the telescope alters how light reaches the sensor. This can stretch, widen, or inflate faint objects. When 3I Atlas was observed under marginal conditions, those atmospheric distortions were interpreted by some as signs of anomalous structure, but observatories operating under optimal conditions demonstrated that those effects were completely external to the object. Taken together, all these causes, digital noise, color filters, compression, saturation, atmospheric distortion, internal scattering, psychological expectations, and uncalibrated equipment, explain why 3I Atlas appeared strange in popular images but completely normal in scientific analyses. What many interpreted as signs of rarity were, in reality, visual artifacts that did not reflect the physical nature of the object. The true lesson is that the appearance of an astronomical object in public images does not always represent its real structure. And in the case of 3I Atlas, this difference between appearance and reality fueled the narrative of mystery when what lay behind was simply the physics of observation and the limits of instruments. The comparison of 3I Atlas with other interstellar visitors was inevitable from the moment its hyperbolic trajectory was confirmed. The public, accustomed to the narrative surrounding Oumuamua and later Borisov, expected each new interstellar object to bring a deep mystery, unusual behavior, or a direct challenge to existing astronomical theories. However, this expectation ignored that those two objects represented extreme cases within a much broader spectrum. When 3I Atlas began to be examined in detail, it became clear that its nature was very different from its predecessors, and that difference helped reveal why many considered it disappointing. The first logical comparison point is Oumuamua, the most famous interstellar visitor so far. Its behavior generated global debates because it showed a non-gravitational acceleration that could not be immediately explained by classical mechanisms. Its reflectance was also atypical, its light curve anomalous, and its shape appeared very elongated. All this led to multiple hypotheses, some more speculative than other. But it is fundamental to understand that Oumuamua does not represent the norm, it represents the exception. Its combination of unusual characteristics occurred under extremely specific circumstances, and many scientists consider its behavior explainable by uncommon but not impossible physical processes. In the case of 3I Atlas, nothing in its behavior indicated anomalous acceleration. Its trajectory was completely compatible with an icy body subject only to solar gravity. It presented no unexpected variations or abrupt changes, placing it at the opposite extreme from the Oumuamua case. Regarding chemical composition, the difference with Borisov was equally clear. Borisov was a highly active interstellar comet with significant emissions and a perceptible extended coma. Its spectra revealed the presence of abundant volatile materials, indicating its internal structure was relatively well preserved despite its interstellar trajectory. Additionally, it showed unusual levels of certain compounds that aroused scientific interest for their possible implications in formation processes in other systems. 3I Atlas, on the contrary, showed no notable activity. Its coma was faint, its volatile emission minimal, and it did not exhibit the same richness of detected compounds as Borisov. This indicates that both bodies, though sharing interstellar origin, had completely different histories. Borisov probably spent less time exposed to galactic medium where, while 3I Atlas appeared to have been eroded for millions of years. The comparison between cometary activity is also revealing. Borisov began sublimating actively long before approaching perihelion, showing clear signs of gas and dust release. Its behavior was similar to that of a young comet within the solar system, reinforcing the idea that its volatile reserve was well preserved. In contrast, the activity of 3I Atlas was so low that many instruments struggled to distinguish its emission from the background. The absence of a prominent tail, intense jets, or eruptive events demonstrates that the amount of volatiles remaining inside was extremely small. This type of difference explains why Borisov was catalogued as an active interstellar comet, while 3I Atlas was more correctly described as a worn icy body. Another key comparison element is shape. While Oumuamua's light curve suggested highly elongated geometry, that of 3I Atlas revealed more typical behavior. Its brightness variations were smooth, without the extreme patterns accompanying objects with pronounced elongations. This indicates that its shape, while irregular like most small bodies, did not present extraordinary characteristics. In practice, this aligns much more with little active solar system asteroids or comets than with an extreme object like Oumuamua. Many early images that seem to show elongated geometry were the result of instrumental limitations, not real shape. From a dynamic viewpoint, the comparison is also enriching. All three objects, Borisov and 3I Atlas, followed hyperbolic trajectories, but the way they interacted with the Sun differed. Borisov reacted like an efficient comet in releasing material. Oumuamua showed unexpected behaviors. 3I Atlas behaved completely predictably. This diversity makes clear that interstellar objects are not a single type of body. They represent a variety of physical, chemical, and dynamic histories depending on their origin, age, and time spent in interstellar space. The apparent density of 3I Atlas also contrasts with its predecessors. Studies of Oumuamua suggested it was extremely light, possibly porous or even formed in thin layers, which could explain its unusual acceleration. In the case of 3I Atlas, evidence pointed to a more compact and hardened object, consistent with a solid internal structure that had withstood millions of years of impacts and erosion. This structural difference contributed to the object not exhibiting dynamic behaviors outside the ordinary. Even surface reflectance served as a comparison point. Oumuamua had a peculiar albedo that puzzled astronomers, while Borisov showed brightness compatible with active comets. 3I Atlas, for its part, had a dark and dim surface, consistent with bodies coated in hardened carbonaceous materials typical of long exposures to cosmic radiation. In other words, its reflectance was perfectly within expected ranges, without surprises or anomalies. Finally, the comparison between the three objects demonstrates something fundamental. Interstellar visitors do not form a uniform category. Not all will be extraordinary. Not all will show rarities. Some, like 3I Atlas, will be silent messengers that confirm models instead of challenging them. This is as important for science as the presence of anomalies, because it helps build a complete picture of how interstellar bodies behave in general. While Oumuamua left open questions and Borisov offered a view of an active young interstellar comet, 3I Atlas provided the necessary counterpart, evidence that many interstellar objects can arrive in the solar system in an advanced state of erosion, with little activity and completely predictable characteristics. Its value lies not in the extraordinary but in the consistent. And that consistency is essential for understanding the true diversity of materials traveling through the galaxy. The scientific value of 3I Atlas is not found in the spectacular, but in what it reveals about the general nature of interstellar objects and the processes governing the formation, degradation, and evolution of solid bodies beyond the solar system. Although many people expected a visitor full of mysteries capable of challenging theories or presenting never-before-seen behaviors, scientific reality turned out to be very different, and it is precisely that difference between expectation and evidence that gives rise to a profound conclusion. 3I Atlas is important not for what it has that is extraordinary but for what it confirms about the universal. The first significant contribution of 3I Atlas is that it supports the hypothesis that the formation processes of icy bodies in other star systems are not radically different from those occurring in ours. Its composition based on simple molecules like diatomic carbon, degraded organic fragments, and darkened particles matches what is observed in aged solar system comets. This suggests that on a galactic level, the basic chemistry governing the formation of small objects repeats on a large scale. The presence of common components indicates that protoplanetary disks around other stars probably contain similar materials and follow analogous aggregation and evolution processes. Another crucial point is what 3I Atlas confirms about interstellar erosion. The extremely low observed activity, together with the lack of available volatiles for sublimation, offers direct evidence that bodies spending millions of years traveling through deep space progressively lose their energy reserves. High-energy cosmic radiation, constant bombardment by charged particles, and collisions with interstellar dust grains slowly degrade the most sensitive molecules, break complex chemical bonds, and transform surfaces originally rich in ice into hard, darkened, and chemically simplified layers. This process is difficult to study in a laboratory due to the involved time scales, but objects like 3I Atlas function as direct witnesses to these mechanisms. The fact that the object showed no intense activity also helps refine sublimation models in interstellar bodies. Many theoretical models assumed that an interstellar object approaching the Sun for the first time would exhibit eruptive behavior due to the presence of fresh material. However, 3I Atlas demonstrated that this depends deeply on the object's prior history. If the nucleus has already been eroded for millions of years, the volatile reserve may be too low to generate observable activity. This forces astronomers to revise previous models and consider that the diversity of behaviors among interstellar objects is probably much greater than initially thought. The analysis of 3I Atlas also contributes to understanding how interstellar objects behave dynamically. Its hyperbolic trajectory was totally consistent with solar gravity, without unexpected behaviors or hard-to-explain accelerations. This confirms that most interstellar objects will move predictably when entering the solar system. Unless they possess very specific physical properties, as in the exceptional case of Oumuamua, knowing that the majority will follow regular dynamics helps astronomers calculate future trajectories, predict encounters, and plan more detailed observations when new interstellar visitors appear. Another important contribution of 3I Atlas is its relevance in studying the size distribution and physical characteristics of interstellar objects. While some like Borisov arrive in an active state and others like Oumuamua present extreme geometries, 3I Atlas represents a distinct type, a moderately compact body with irregular but not extraordinary shape, without significant activity, and with a hardened surface. This expands the available sample and helps build a more representative picture of the real population of interstellar bodies. Before these discoveries, humanity only knew objects created within the solar system. Now, thanks to these visitors, it is possible to observe and compare structures formed elsewhere in the galaxy. Additionally, the fact that 3I Atlas presented no spectacular anomalies is a contribution in itself. It confirms that not all interstellar visitors need to challenge existing theories. Science advances not only from exceptions but also from confirmations. Every interstellar object that fits within models reinforces their validity and reduces uncertainty about how physical processes work in deep space. The thermal behavior of 3I Atlas also offers key information. Its response to increased solar radiation was moderate and stable, supporting thermal models indicating that interstellar bodies with hardened surfaces release heat gradually and balanced. This helps astronomers understand how energy is distributed in these objects and how surface layers behave when passing from extremely low temperatures in deep space to higher temperatures near the Sun. Another relevant aspect is that 3-eye atlas serves as a reference for improving observation techniques. Many interpretation errors in early images showed the importance of properly calibrating instruments, understanding the limits of astronomical photography, and distinguishing between visual artifacts and real structures. The object's analysis also forced a review of how to interpret low-signal light curves and how to estimate shapes when available information is limited. This experience will be invaluable when new interstellar objects with similar or even weaker brightness are detected. Finally, 3-eye atlas contributes to a more realistic understanding of what to expect when humanity detects interstellar visitors in the future. Not all will be spectacular, not all will show unusual behaviors, not all will generate bright tails or intense activity. Some will be silent, eroded, and moderate like 3-eye atlas. And that diversity of behaviors is fundamental to understanding the true nature of materials traveling through the galaxy. Science, far from seeing this as a disappointment, interprets it as an opportunity. Every interstellar object, active, inactive, strange, or common, provides necessary pieces to reconstruct the history of how solid materials form and evolve in different galactic regions. 3-eye atlas did not break models. It confirmed them, and in doing so became a key piece for understanding that the physical principles of the cosmos are indeed universal. As the scientific community finished analyzing all the data obtained on 3-eye atlas, a more mature, complete, and realistic understanding emerged about its meaning. It was not the kind of interstellar visitor many imagined when they first heard its name. It did not present explosive activity, did not show exotic chemical signals, did not exhibit impossible shapes or mysterious dynamic alterations. Nor did it challenge established models or force complete theory rewrites. But that apparent normality, which for some became a disappointment, is precisely where its most important contribution to modern scientific knowledge resides. The final part of the 3-eye atlas analysis consists of understanding what its passage through the solar system truly represents. For those seeking a spectacular phenomenon, its dim behavior seemed anticlimactic. But for astronomers studying interstellar objects, its existence confirms an essential perspective. The majority of bodies traveling between stars will not be extraordinary. They will be natural products of distant planetary systems, formed under conditions similar to ours and shaped for millions of years by the same universal forces that affect all icy bodies in the cosmos. Its presence established a key point in interstellar object statistics. With Oumuamua, an anomaly difficult to fit was obtained. With Borisov, an active comet that seemed freshly emerged from a young system was obtained. But with 3-eye atlas, something that was missing was obtained: evidence of a highly eroded, dim interstellar body with minimal activity. This demonstrates that interstellar objects can present a wide range of evolutionary states. Some will be young, others ancient. Some will have fresh surfaces, others will be deeply degraded. 3-eye atlas represents one extreme of that spectrum, one that needed to be observed to complete the understanding of the phenomenon. Its scarce activity also helps redefine how future detections should be interpreted. Before this object, it was believed that an interstellar visitor would activate strongly when approaching the Sun. Now, scientists know this is not always true, that activity depends on the object's thermal history, time spent in the interstellar medium, degree of surface erosion, and how many volatiles survived that journey. This will allow future predictions to be more accurate, avoiding expectations based solely on parallels with solar system comets. Another important aspect of 3-eye atlas was its simple chemistry. Its spectrum showed signals consistent with widely known materials. There were no surprises, no unexpected compounds or molecules that questioned current knowledge about formation processes in protoplanetary disks. For some this was disappointing, but from a scientific viewpoint it means something much deeper. It confirms that solid matter in the galaxy follows the same fundamental rules in different regions, that the physics of carbon, ice, dust, and radiation does not change drastically between stars. This suggests that the galaxy, despite its immense size and diversity of environments, can present surprising chemical uniformity at its most basic scale. The dynamic behavior of 3-eye atlas also provides crucial information. Its trajectory, completely consistent with gravimetric models, confirms that most interstellar visitors will move predictably. There will not be sudden accelerations or mysterious deviations in every case. This allows future observation methods to be designed with greater confidence, anticipating where these objects will be at each moment and improving the probability of studying them in greater detail at early stages, when they are still far from the Sun. Even its light curve, one of the most important tools for studying its shape, confirmed the stability of an object without extreme characteristics. This allows better calibration of theoretical models about how interstellar erosion affects the geometry of small bodies. If 3I Atlas had shown impossible elongations, it would have been difficult to reconcile with existing models. Instead, its geometric consistency reinforces current concepts about compaction, hardening, and wear of icy surfaces after spending so much time outside planetary systems. 3I Atlas also had an indirect but significant role. It forced a review of how astronomical images are interpreted in the digital era. Its case demonstrated that photographs obtained by non-professional cameras can easily induce visual errors mistaken for real structures. This has led the scientific community to further emphasize the importance of verifying data with calibrated instruments before drawing conclusions. The experience with this object will serve as a basis for communicating more clearly with the public when new interstellar visitors appear, explaining the difference between what an image seems to show and what scientific data actually indicate. One final contribution of 3I Atlas is both philosophical and scientific. It demonstrated that the value of an interstellar object does not need to lie in spectacularity. Its importance resides in the incremental knowledge it provides, in how it confirms patterns, supports theories, refines models, and expands understanding of the universe. Not every interstellar visitor needs to be an unsolved mystery. Some, like 3I Atlas, are pieces that fit perfectly into the puzzle, helping complete the bigger picture of how matter behaves between the stars. For those expecting something extraordinary, the conclusion was disappointing. For science, the conclusion was valuable. 3I Atlas was not a spectacular event, it was a silent confirmation that physics works consistently even on galactic scales. Its passage did not leave explosive headlines, but it did leave a clear scientific record. Interstellar objects are not solely anomalies or rarities. They are common messengers from remote systems, carriers of solid information about how matter forms and ages in the universe. And that is ultimately the greatest lesson it left. The extraordinary is not always in the surprising, but in the consistent.